Our next speaker is Percy Liang. Percy is Assistant Professor of Computer Science and by courtesy of Statistics. So Percy?
Thank you. Hi, thanks everyone for coming. So I'm going to share with you a new perspective on connecting machine learning and natural language processing. So it's well known that the field of natural language processing has made enormous progress in recent years. We now have systems that can recognize speech and power digital assistants, systems that can translate between hundreds of languages, and systems that can answer questions from text, which is something that our research group has been interested in lately. And driving all of these kind of successes in natural language processing is machine learning and the advances in there. But I'd like to turn things around a little bit for the purposes of this talk and think about not language, learning for language, but learning from language. And to set the stage for this perspective, I want us to think about language, not passive text waiting to be analyzed, but rather an active communication system that humans invented tens of thousands of years ago to help us survive. So here's how machine learning works in a nutshell. So you show a machine learning algorithm a lot of examples. So in this particular case, we have colored bars. Each colored bar is either a 1 or a 0. So now I ask you the question, can you figure out what is the thing that distinguishes the ones from the zeros? Okay, so maybe that's not such an easy task, and while machine learning algorithms can process this data much more effectively, it still has to do a lot of work to figure out what is the hidden concept. Now, how would you do this in natural language? You would just simply say the ones are at least the ones where there's at least 2 red squares. So this shows the power of language, the ability to access the concepts directly, more succinctly, and leave less to kind of statistical chance. And it's also just a more natural and human way of teaching. So I'm going to talk about 2 ways that we've implemented this general idea. The first in the context of information extraction. So the goal is to take large volumes of the text and mine information in a structured way. So in this particular example, we're trying to figure out whether 2 people are married based on reading the passage. So traditionally, what you would do is get a bunch of annotators to look at this data and read it and answer yes or no, are the 2 people married? And you can imagine this is very labor intensive, but moreover, you're only getting a single bit of information, a yes or a no, from all this hard work. So let's do something else. Let's go a little bit farther and ask the annotator, so why did you think so? Can you provide an explanation? Can you show your work? And so the annotator in this example might say, well, because the words his wife are a kind of a strong cue here. So we took these explanations, and then we used semantic parsing to convert them into programs, a language that computers can understand. And we can run these programs on lots of unlabeled examples, and in the process, create a giant but somewhat noisy data set, which we can use to train a model. So we experimented with several different domains, and overall, we were able to get the same level of accuracy using these explanations as opposed to labeling yes or no. But even taking into account that explanations take longer, we were able to get a 3 to 50x improvement with explanations, showing the power of kind of natural language. So here's another example. Suppose you're a graphic designer and you wanted to construct beautiful 3D scenes out of little primitives. So it would be nice if you could speak to your assistant and say, add 2 chairs 5 spaces apart and have this wonderful scene just appear. But this task is very complicated if you want to build it up from the very small building blocks, and current machine learning algorithms would simply fail on it. But what would a human do? If you were trying to tell someone how to do this, you'd probably try to explain it. So, okay, you add a chair, move 5 squares to the left, and add another chair. But moreover, if people don't understand what chairs are, you can elaborate and recurse and say, okay, a chair has 4 legs, a chair base, and a chair back. And so in this kind of very adaptive way, you're beginning to teach the system in a more flexible and hierarchical way than simply saying kind of a yes or a no. So here's an interface we built, a prototype system where the user is trying to accomplish a goal, build some sort of structure. And the user types into a text box, and if the system understands, then all is well, the user gets his palm tree or whatever he's trying to build and moves on. If the system doesn't understand, then there's a learning opportunity here. The system can explain, here's how you build a palm tree. And in the process, the system gets better on the fly over time. And in addition, the user still gets his palm tree. So this is kind of a win-win situation here. So we ran this pilot study on Amazon Mechanical Turk over 3 days, and I was simply blown away by the amount of creativity that people have online. They were able to build these amazing types of structures, but in the process, teaching the system a language that helped them be more productive at doing so. So to conclude, I want you to take away that language is this powerful tool for communication that we've been using effectively as humans to humans, but I think it's an important opportunity to infuse this capability for human-machine communication as well. We've shown that by allowing people to provide explanations or definitions, we can dramatically speed up learning. But I want to point out this is only the very beginning. There's many hard research problems here, but also many opportunities to improve learning and make it more transparent and effective. So thanks.